We want to talk about a really classic example of a problem that has to do with improper integrals. This problem is going to be about a mathematical figure called Gabriel's horn. So let's see, what is Gabriel's horn? Okay, so we want to see first, what is Gabriel's horn, right? So here are my x and y axes, so x and y. And what I want to do is plot the curve y equals 1 over x. Right, so the curve y equals 1 over x looks something like this. So y equals 1 over x. And then I'm going to be interested in that curve from x equals 1 all the way to infinity. Right, so I have this piece of the curve all the way to infinity. And what I want to do is rotate around the x-axis. So the other side of the curve looks something like this. Right, and so you can see that when I do this rotation, what I get is this sort of infinitely long thing that sort of looks like a trumpet, right? So this is Gabriel's horn. Now that we've seen what the horn actually is, let's go ahead and see if we can calculate the volume of this horn. This will combine some of the ideas that we've had before, rotating an object around the x-axis, as well as the improper integral. So let's go ahead and find the volume of Gabriel's horn. All right, so I want to set this up, right? What I have are my little discs, this time around the x-axis, right? And so what is the height of the cylinder? Well, in this case, it's just a little bit in the x direction, so we'll call it dx. And then what is the radius of my cylinder? Well, the radius goes from y equals 0 to the curve, and so the radius is the y measurement, which in terms of x is 1 over x, right? So the volume of my little cylinder here, each one of them is, well, how do I take the volume? It's pi times the radius squared times the height, which is dx. And where do I want to add up all of these cylinders? Well, I want to start at x equals 1, and I want to go all the way to x equals infinity. So the volume of Gabriel's horn is given by the integral from 1 to infinity of pi times 1 over x squared, that's my radius squared, dx. Okay, so let's go ahead and evaluate this integral. It's an improper integral, so I go ahead and use some value here, and I take the limit. So what I get is the limit as maybe a approaches infinity. I have constant pi. I'm integrating from 1 to a, and I have x to the -2 times dx. All right, so I'm going to evaluate this integral. And what I get is I have still the limit as a approaches infinity. I have pi, that's my constant. If I integrate x to the -2nd, that's just a power of x, so I get -1 x to the -1, and I'm going to evaluate this thing from 1 to a. So I get the limit as a approaches infinity. I have pi times -1, so maybe we'll put negative pi. So then this is x to the -1, so I have a to the -1 minus 1 to the -1. So this is the limit as a approaches infinity of negative pi times 1 over a minus 1. Okay, so now what happens as a goes to infinity? Well, as a gets really large, this piece of my equation gets closer and closer to 0. So this goes to 0, and 1 just stays itself, so the limit of this thing is negative pi times -1, or just pi. So the volume of Gabriel's horn, this infinitely long trumpet-looking thing, is actually equal to pi. So we found that the volume of Gabriel's horn is actually a finite number. This is pretty crazy. It's an infinitely long object that has finite volume. But the story gets even crazier. Let's see if we can say anything about what the surface area of Gabriel's horn should be. Finally, let's calculate the surface area of Gabriel's horn. I have my little disk thing here, and this is not exactly how you calculate the surface area. If you want to look up how to calculate surface areas of solids of revolution, I encourage you to do that. But I can think sort of just about what is the surface area of my little disk, right? If I was actually going to calculate the real surface area, I would not use just dx for the side of it. I would use this little piece of arc length here. That integral is a little more complicated, and so we're going to just work out this one that sort of approximates the surface area, but you'll still get the same answer if you use the real surface area calculation. Okay, so what is the surface area of a cylinder? Well, I don't really need to count the top and the bottom because I really only want the thing sort of around the outside of Gabriel's horn. So if I unroll my cylinder, right, I have this cylinder whose height is dx and whose radius is 1 over x, right? If I sort of unroll it, it will unroll into this long rectangle, right, whose height is still dx, but now this side is the circumference of my cylinder. All right, so what's the circumference? Well, circumference is equal to 2 times pi times the radius. So this is 2 pi times 1 over x, right? So then the surface area of my cylinder would be 2 pi over x times dx, right? Because that would be the area of this rectangle. And then I want to add up all of these little rectangles, right, cylinders, all the way from x equals 1 to x equals infinity. So let's go ahead and calculate the surface area. So the surface area, I take the integral from 1 to infinity of the surface areas of my little cylinders, 2 pi over x times dx. And what am I going to get? Well, this is an improper integral again. So this is the limit as a approaches infinity. I'm going to integrate from 1 to a. And then I have a constant 2 pi that I can pull out of the integral. And then I just have 1 over x dx. And how do I integrate 1 over x dx? Well, I know that one. It's the natural log of x, or natural log of absolute value, but everybody's positive, so we don't have to worry about that. So this is the limit as a approaches infinity of 2 pi times the natural log of x. And I'm going to evaluate from 1 to a. Okay, so what do I get when I evaluate this? I get the limit as a approaches infinity. I have 2 pi times the natural log of a minus 2 pi times the natural log of 1. Well, the natural log of 1 is actually equal to 0. So this piece is equal to 0. And as a gets bigger and bigger and bigger, so does the natural log. So this goes to 2 pi times the natural log of something getting really, really big, which is really, really big, right? And so what I actually get is infinity. So that the surface area, this is really only approximate, right? Because I didn't use the actual surface area calculation. But the surface area of Gabriel's horn is infinite. So we found that the surface area of Gabriel's horn is actually infinite, even though the volume is finite. This seeming paradox between finite volume and infinite surface area is why Gabriel's horn has fascinated mathematicians for a long time. Hopefully, this has been an interesting problem for you to think about, and I hope that if you have a question, you post it on the forum. Good luck.